I'm Yinoussa Adagolodjo, and I'm a member of the FROST team. This work is the collaboration with Federico Randa, which is a doctor, professor assistant in Abu Dhabi. The motivation of this work, of this presentation, is just to propose a new tool for soft robot modeling in Super. Because today we have many tools, we have many choices when possibility for the design of soft robot by the choice of the actuators or how we transmit forces inside the structure or the use of material with different stiffness. However, we have very few tools, or just say quite poor tools, especially when it comes to model the mechanical. When we have to model the mechanical of the mechanics of soft robot. And so far, we just can say that two methods have really emerged to successfully model the mechanics of this robot while taking into account the material properties. The first one is based on Coursera theory, which has the advantage of having formulation close to the serial rigid robot using reduced coordinate. But here, in this work, we mainly focus on the PCS, which is the work done by Dr. Randa. The main, like they say, the main assumption of the method is to model the formation of a soft manipulator arm. We use the finite number of sections, and assume that on each section we have like a constant strength along each section. The advantage of this method is you can still model the torsion of the soft arm. You can model the inextensibility of the rod or the cable when you don't want to model, when you don't want to take them into account in your model, which is very difficult when you are using some methods like finite element method. And the main limitation is that when you have to model like stress structure or complex geometry or volume deformation, it's very difficult with this method. And the second method, also able to model this deformation, take into account the mechanical properties, is the finite element method, often represented by the position and the velocity of a set of connected nodes. The advantage of this method is that you have the freedom on object geometry, like you can use the method to model beams, shell element, or deformable volume. You also have the you can also define freely the material positive law. You have the facility to choose the boundary condition, which can be very interesting when you are doing soft robot. And also you can connect beams to create the stress structure, which is very difficult when you are using finite element, when you are using PCAS or theory or Coursera theories. But the main limitation of the method is when you have when we are modeling like cable, inextensible cable, you have to add some additional constraint in order to remove this inextensibility. Here, the goal of this work, the goal of the plugin we propose is not to challenge these two methods. The goal of this work is just to take advantage of each one in order to propose a new plugin for the modeling of this soft robot. And in the following, I will just show, like, I won't go into detail for the DCM or the method of DCM or finite element method. If you need some more explanation, we have we have a paper about that we publish. Then you also have the work of Federico, and then you can look on what he did, or if you want, we can also talk about it after. I will just show you some example and how we combine this method, how we made the bridge between this method. Since the first one, we will use the Coursera theory to model the 1D object, like the cable or the rod when we use them to actuate soft robot. And the 3D structure will be modeled using the finite element method. Here, the advantage of the DCM or PC-wise is chess-wise constraint is to use the reduced coordinate to model the cable or the soft arm, and the global the finite element method is in the global frame. To make the bridge between these two, we just use the Lagrangian constraint to make the bridge. Then we create some constraint points between this cable and the 3D constraint. I will show you some videos to show how it works. Here we just have to make the also come from the reduced coordinate to the global frame. We use Jacobian to make the transition between this information. And here, as you already know, here we are using Lagrangian constraint to make the bridge between the node space and the constraint space. You still see my screen?
Yes, perfect.
Yeah, I will show you the first simulation. Is here we have a finger which is made model using the finite element method, and the cable which is made model using the finite using the Coursera theory. Behind this, you have like what we call sliding constraint point we define inside, and here this is the auto collision between the fingers. And we did the same thing using 3 fingers. Here the goal is just to grasp a rigid body using 3 fingers, and we are showing here that also we are able to do that in real time. And the advantage of Coursera is using the reduced coordinate. We are able to reduce the time, the computation time, and we can reduce really the size of the figure. Here also, like we are testing our object on the pre-bent cable. We want to use this kind of pre-bent cable to drive a finger again. See that compared to the first thing, we don't have the same deformation of the finger. Here we deform the finger not in the plane, but out of the plane of the X of the finger. We do the same thing using 4 cables to deform a trunk. Here we are using the inverse method. The inverse method, the goal is to just follow this. I'm coming. The goal here is to follow this. I'm solving an inverse to follow this this yellow balloon. Then we are using 4 cables to do that, and as you can see behind here, automatically we know on which cable we have to pull in order to follow the target. And the advantage here is we don't need to add some constraint like as we do in normal with finite element cable. We don't add any constraint to avoid the inextensibility because we are using inextensible cables. Here I am not presenting how we model the inverse part because I only have 10 minutes. I hope I still have time.
Yeah, but 1 minute left if you like.
Okay, but that's I think. So if you have some questions.
Thank you very much, Younes, for the presentation. More than in time. Yeah, is there any question for Younes for this cable model? Yeah, François is asking a question. Do not hesitate also to unmute yourself. I don't know if you have a mics and so on, but really it's open. When it's open time for questions, really do not hesitate to unmute yourself and take the mic and directly ask the question.
Hello guys, everyone. Can you hear me?
Yeah, perfect.
All right, Yes. Thank you very much for this talk. Yeah, I was wondering, but it's not really a question, but more a general topic related to Coursera models. Is just if you've considered or if you tried or know in the literature, like the models that were developed by Florence Bertals, which I think share very similar properties as the one that you mentioned, which basically use SuperLeaks models. That's Damien Marshall or Super Clotoid. Anyway, it's just models where also like the general degrees of freedoms are the curvature, I think, and there is some essentially like the material properties or the way like the the movement is discretized is it's like a constant or piecewise linear function of the curvature, and then you can derive based on that like the afterwards like the positions of the rod you want to simulate, and it shares the similar properties. I'm not sure if that it's inextensible by design as well.
Okay, I don't know the method, but yeah, I will check to see. Yeah.
Okay, I happen like to have attended like a seminar by Florence. Hugo was there as well last week, and so it reminded me of that. And I think like the code is open source for that. So I'm not sure it's a C++ code. I think it's a Python code, but anyway, it just I think it shares a similarity. So maybe it's interesting to have a look at.
Okay. What I just want to say is, yeah, the code is open source and it's on GitHub. Yeah, maybe after we will show that, but I already stopped sharing my screen. Yeah, there also you have some document. I put some PDF, I put some images and some test scene if you want to trace, and I'm still available if you have some questions.
Yeah, I saw that yesterday actually that you put your the code on GitHub. So yeah, I'm very excited to test it. And yeah, thanks again for the talk.
Yeah, if you want to test this, yeah.
Is there any other question in the meantime? So do not hesitate to unmute yourself again, just for information, because that's exactly what Yinoussa has just said, is that this year, again, like previous year, so it's actually the second time that we're organizing that, there is awards, contributions awards for people that are providing open source contributions. We are lucky because this year we had 6, and I must say 6 very good contributions that has been proposed as candidates for the awards, and there will be 2 prizes. First, there is the organization committee prize that has already selected some contribution, but there is you as the public. You can vote for the open source contribution you prefer the most, and one of them is actually the COSRA model that Yinoussa just presented. It's an open source plugin that is available. Anyone can use it, test it, assess it, and so on. Maybe I have just a few seconds left. Yinoussa, I would have a question. So is that completely ready to use and not only for I would say cable purposes, but for any wire-like simulation that you'd like?
Yeah, that's what I presented before. That's you can use it because I already tried to use it like a needle. I'm doing it right now. Then normally it works. Yeah, we can use it as a needle, but the only thing is to know how to add constraints to make the choice of the constraint. And with Christian also, we develop a new mapping techniques, which is simplify the use of the plugin. And we can have the talk about that maybe tomorrow or something like that. And yeah, if you have a new contribution or to propose something new to make it better about the code, I don't know, but yeah. Normally you can use it for cable, you can use it for catheter, you can use it for anything.
Needles, catheters, cables. Okay. Thank you very much, Yinoussa, again. I think I would have other questions like about performances and so on, but I'll wait for
Normally it's real time. Yeah.
Okay.
And I'm using it for like to implement some implants. And like as you see for the trunk, we have 4 cables and it's running in real time. Then for me, I think that's and 4 cables with like 99 constraint, fixed constraint. So normally, it's real time with that.
Thank you again, Younes. Stefan, it will be indeed your turn. So thank you again, Younes. There will be time for questions just after Stefan's presentation. You could ask actually questions further to Van, to Younes, and to Stefan. But before this short break, there will be the presentation about model-based TensorFlow